All right, today we're decoding a kind of secret language, a script, really, that tells programs how to behave when they're designed to run, well, forever. It's called Linear Temporal Logic, and it's basically the rule book for some of the most critical technology we use every day. Okay, so let's start with a question. What do a pacemaker, the little engine controller in your car, and a Mars rover all have in common? I mean, they seem totally different, right? But there's one thing that connects them all. Well, the answer is that their software isn't supposed to stop, ever. It doesn't just run a task and then close. No, it's designed to run continuously, always reacting to what's happening around it. And, that creates a huge challenge. How on earth do you prove that a pacemaker will always keep the right rhythm, or that a rover will never accidentally drive off a cliff? So to figure that out, here's our game plan. First, we'll get a handle on these programs that never end. Then, we're going to use a really cool analogy, a script for infinite time. After that, we'll dive into the grammar of forever, see how it ensures systems are both safe and responsive. And finally, we'll look at the incredible legacy of this idea. Right, so these non-stop programs, computer scientists call them reactive systems. And you interact with them all the time. Think device drivers, network servers, even the controller for an industrial robot. They're just stuck in this constant loop. Wait, react, update. And that means checking if they work correctly isn't about looking at some final answer. It's about checking their entire, literally infinite behavior. And this is the exact problem that a computer scientist named Amir Poelli was staring at back in 1977. He realized he needed a whole new tool. He needed a formal language, basically a kind of mathematical logic, built from the ground up to talk about the behavior of these ongoing programs. Okay, so how does this logic actually work? The best way to get it is with a really simple but powerful analogy. We're going to think about these programs in a completely different way. I want you to imagine the entire, endless execution of one of these programs as a movie that never ever ends. It just keeps playing. And every single moment, every state the program enters, that's just one frame in this infinite movie. And this is where it all clicks together. See, that infinite sequence of states the program goes through, that's just the sequence of frames in our movie. The program's overall behavior, what it actually does over time, well, that's the plot of the movie. And here's the kicker. If you want to control the plot, what do you need? You need a script. And linear temporal logic, that is the language we use to write the script. Okay, so if LTL is the language for our script, what's its grammar look like? Turns out it all comes down to just a few core ideas, what we call temporal operators, that let us make really specific rules about time. First up, we have G, which stands for globally, or more simply, always. This is the big one, the ultimate rule. When you write a G rule, you're saying some property has to be true in every single frame of the movie, from the very beginning to infinity. No exceptions, ever. Then we've got F for finally or eventually. You can think of this one as the optimist. It doesn't say something is true right now, but it makes a promise. That property will be true in at least one frame in the future. It has to happen eventually. Next up is X, and it just means next. Super simple. It's incredibly precise. It makes a claim only about what's true in the very next frame of the movie, the immediate next step, and nothing else. And last but not least, we have U for until. Now, this one's a little different because it connects two things. It says, okay, this first thing must be true, frame after frame after frame, until this second thing finally becomes true. It sets up a condition. So we have this grammar, right? Always, eventually, next, and until. But so what? Why is this so incredibly powerful? Well, it's because with just these few simple building blocks, we can write the two most important kinds of rules you could ever want for a critical system. And they fall into two big categories. First, you have safety properties. These are all about making sure that something bad never happens. They almost always use that big G operator for globally. For instance, a rule might say, globally, it's true that two trains are not on the same section of track. Then you have liveness properties. These are the flip side. They promise that something good will eventually happen. They use the F operator. So a rule might be, eventually, the request you sent will be granted. And here's the crucial part. You absolutely need both. Think about it. A system that's safe but has no liveliness is like a traffic light that's stuck on red forever. Sure, it's perfectly safe, no one's going to crash, but it's also completely useless. Liveness is the guarantee that the light will eventually turn green. You need safety to prevent disasters, and you need liveness to actually get anything done. So where did this idea go? Well, what started in an academic paper back in 1977 definitely didn't stay in the classroom. It grew into a foundational pillar of how we build reliable technology today. You can really see its journey play out. It all starts in 77 when Amir Poelli introduces it. Then by 1985, people like Sisla and Clark had figured out the deep mathematical complexity of checking these rules. And fast forward to today, LTL is the direct ancestor of even more powerful logics that can reason about things like precise timing and really complex behaviors. So why does any of this matter? Well, because LTL and logics like it are the engine behind something called formal verification. That's the automated process of checking our software and hardware designs against these kinds of scripts. It lets us find these really deep, subtle, and frankly dangerous bugs in complex systems before they ever get shipped in the products we all depend on. And that brings us to a final thought. All these systems we rely on, the pacemakers, the cars, the power grids, they are all running on an infinite script. And that means someone, somewhere, had to sit down and write the rules. They had to decide what was most important. So think about it. For the systems in your life, what rules do you think matter the most? Safety or liveness? The tricky part is, the answer is always both. And now, you know the language they use to write those rules.